The Science of Motion, Stage 4, the Machines and Application of the Principles and Laws of Motion. Welcome to the virtual class of the Science of Motion. In this stage, we will talk about simple machines, such as the lever, the inclined plane, the pulley, and the wheel and axle. As we approach the topics, you will realize that even though they were used since ancient times, they are still very useful in our times. In addition, we will talk about compound machines and their components. Remember to have your calculator with you to solve the examples. The objective of these machines is to facilitate men's work, transforming an input force into an output force. The input force can be provided by men, and the output force usually produces the movement of a heavy or voluminous body. Some simple machines are the lever, the inclined plane, the wheel and axle, and the pulley. Machines are devices that are used to modify, transmit, direct forces, and carry out a task or a specific job. In all cases, we can consider that the input force is transformed into an output force. It can change the direction of the applied force, multiplies, in some cases, the applied force. It can increase the velocity of operation, and the magnitude of the applied force can be increased along an determinate distance, but at cost of decreasing the distance traveled by the load. This is known as mechanical advantage. Now we will describe some simple machines, starting with the lever, which is a rigid bar gyrating on a point of support, also called fulcrum. In a lever, the distance that exists between the point of support or fulcrum and the point where the effort force is applied is called effort arm. And the distance that exists between the fulcrum and the point where the load to be moved is placed, that is, the load force, is called resistance arm. With respect to these elements, the levers are classified in three types. First class lever. In this type of lever, the fulcrum is located between the effort force and the load force. This lever is the most common and the simplest. These are some examples of first-class levers. Second-class lever. In this type of lever, the force to be overcome, the resistance, is found between the fulcrum and the input force. As can be observed, the effort arm will always be larger than the arm of resistance. This generates that the movements will be in the same direction. Examples of this lever are shown below. Third-class lever. In this type of lever, the input force, the effort, is found between the fulcrum and the output force. Another characteristic of this type of lever is that the resistance arm will always be larger than the effort arm. The basic principle of any machine is that of the conservation of energy. In the case of the lever, we have that the input work is equal to the output work, in such a way that the formula of any type of lever is as follows. Effort force times distance of input equals load force times distance of output. In addition, we can define in a lever the ideal mechanical advantage as the relation that exists between the effort arm and the resistance arm. Also, the actual mechanical advantage is defined as the relation between the load force and the effort force, and the efficiency of the machine expressed as a percentage dividing the actual mechanical advantage by the ideal mechanical advantage, multiplied by 100. Let's see the following example. A 3.2 lever will be used to lift a 220 Newton load, 1.2 meters from the fulcrum, if a force of 150 Newton is applied to the end of the lever. Calculate, letter A, the ideal mechanical advantage, letter B, the actual mechanical advantage, and letter C, the efficiency of the lever. The example mentions that the lever has a length of 3.2 meters and the load is located 1.2 meters from the fulcrum. It means that the effort arm measures 2 meters and the resistance arm 1.2 meters. To find the ideal mechanical advantage, you need to divide the effort arm by the resistance arm. Substituting the values, then we have 2 meters over 1.2 meters, resulting in 1.66. For letter B, we need to divide the load force by the effort force. Substituting the values, we have 320 Newton over 150 Newton, resulting in 1.46. For letter C, it asks us to calculate the efficiency. So we need to divide the actual mechanical advantage by the ideal mechanical advantage and multiplying this result by 100. Therefore, we have 1.46 over 1.66 times 100, resulting in an efficiency of 88%. The inclined plane is a simple machine in which a plane surface creates an acute angle with the horizontal, forming an elevation that allows for objects to be raised or lowered. On an inclined plane, the effective or useful work is the one performed when we raise the load vertically, and the actual work is the one that is done when using the ramp or inclined surface. In ideal conditions, these jobs must be equal, according to the principle of conservation of energy. Then, the force necessary to push the load times the length of the plane is equal to the weight of the load times the height of the plane. The ideal mechanical advantage is given by the length of the plane over the height of the plane. The actual mechanical advantage and the efficiency are found with the formulas that we already knew. It is important to mention that the wedge and the screw are simple machines derived from inclined plane. Example: if you want to push a box that weighs 280 Newton over an inclined plane 4 meters long and 1.3 meters of height, what is the force that must be applied to the box to lift it? The formula of the inclined plane is effort force times the length of the plane equal to the load force times the height. Since the effort force is unknown, it is necessary to clear. Therefore, the effort force is equal to the load force times the height over the length. Substituting the values, we have 280 Newton times 1.3 meters over 4 meters, giving us 91 Newton as a result. The wheel and axle is a simple machine that consists of a cylinder or drum on which a rope is rolled up, and which gyrates around an inserted axis, which is joined to a crank whose arm is longer than the diameter of the cylinder, making possible to raise heavy loads with less effort. The algebraic expression from the wheel and axle is as follows: effort force times the length of the crank equal to the load force times the radius of the drum. The ideal mechanical advantage is calculated by dividing the length of the crank by the radius of the drum. In the following example, we need to calculate the weight that a wheel and axle can lift by applying a force of 50 Newton. If the drum has a radius of 15 centimeters and a crank of 40 centimeters, the algebraic expression for the wheel and axle is effort force times the length of the crank equal to the load force times the radius of the drum. In this case, we need to clear the load force, so load force is equal to effort force times the length of the crank over the radius of the drum. When substituting the data, we have 50 Newton times 40 centimeters over 15 centimeters, resulting in 133.33 Newton. A pulley is a system formed by a group wheel and a rope that moves freely on this group. The pulley turns freely around a fixed axis attached to a support. There are two types of pulleys: the fixed pulley is used to raise objects in a more comfortable way, exerting a force in the opposite direction of the movement of the lifted object. Its ideal mechanical advantage is 1, since the effort arm and the resistance arm are given by the radius of the pulley. To raise an object using the fixed pulley, a force equal to the weight of the object needs to be applied. In the mobile pulley, one of the strings of the rope is tied to a fixed point and the load to be raised is joined to a pulley by a hook, while the other string of the rope is where the effort force is applied to raise it from an upper part. Its ideal mechanical advantage is 2, because the effort arm is equal to the diameter of the pulley and the resistance arm is equal to the radius of the pulley. Ideally, an object can be raised using a force equal to the half of its weight. Let's see the following example. A mobile pulley with a diameter of 16 cm is used to raise a load of 260 Newton. A force of 150 Newton will be applied to the end of the rope to raise the load. Calculate the efficiency of the pulley. To calculate the efficiency, we need the ideal mechanical advantage and the actual one. We know that the ideal mechanical advantage is 2, since it is a division of the diameter by the radius. And to calculate the actual mechanical advantage, we need to divide the load force by the effort force, resulting in 1.73. In other words, to calculate the efficiency, we need to divide 1.73 by 2 and multiply it by 100, resulting in 86.5%. Simple machines have evolved through time. They have been used to perform tasks each time more complex. So, man's engineering has designed mechanical systems that result in the combination of two or more simple machines, known as compound machines. Compound machines are made up of two types of components. The mechanical components, which are those that are connected between them to transform the energy provided into mechanical energy, such as wheels, gears, axes, belts, among others. And the energetic components, which are the ones that provide the energy for the machine to operate. Among them are cells, batteries, and springs. These are some examples of compound machines. Remember to turn in your activities on time. See you!